Hey everybody, it's Mr. Carr again. Today we're going to be looking at 4-4 day 3. Our focus today is going to be basically modeling with our sinusoidal functions. Okay, so the first case we're going to do with this is just kind of take information about our graph and work it backwards and put it into their graph form. We're going to do an equation then. So write the equation of the sine function with an amplitude of 5, a period of 3 pi, a phase shift of negative pi, and a vertical shift of negative 4. So here's the thing to remember about this one. When writing it out, there's a slightly different version of our sine functions. Normally we said a times sine of bx plus c plus d. But c and b together cause that phase shift. So instead of writing it this way, we're actually going to do it this way in terms of like h and k. Now this has no effect on the d. K and d are the same exact thing. But look at where the h is. Okay? H is inside the parentheses here with b in front of that. This is a slightly different way to model our phase shift going on. So for example, I can technically turn this into the other one by multiplying this b out. If I do that, I have y equals a times the sine of bx minus bh plus k here. This negative bh and the positive c are basically the same thing. Okay, so that's what we're going to use is this version here, because if I tell you the phase shift along with a change in the period, it's going to be much easier to model with this version than the other version we've been doing with. So first thing is amplitude is 5. That's 5 will go out front. Okay, so I have 5 times the sine. Remember, the period is 3 pi. So period is 2 pi divided by b, meaning b is 2 pi divided by the period. So in this case, it's going to be 2 pi divided by 3 pi, which is going to cancel those out, which is just 2/3. So I'm going to have 2/3 right there. Then my phase shift is negative pi. So that moves to the left, which means it's going to be a positive pi here when I do that minus h. Okay. And then we have plus k. So it's a vertical shift of negative 4. So I'll have minus 4 here. Okay. And that is it. I can actually just model it this way and be done. The other thing I could do is I could take the 2/3 and multiply it out so it looks kind of like how we normally will write it. Just be aware that this is equivalent. So like these two are kind of interchangeable here. So if I do that, I'm going to have y equals 5 times the sine. That will be 2/3 x plus 2 pi over 3, and then minus 4 still. Okay, both of those end up with the same exact kind of graph there. All right. The other main thing to focus on is using our regression forms. So we're going to do a sinusoidal regression here. So when you do this, so first thing is if you're going to use a graphing calculator, it works exactly the same way. You're going to have L1 and L2. So we're looking at the average monthly high temperatures for Chicago. If X1 is going to represent January, so that's 1, 2, 3, so on up to 12. Okay, so make that your L1, your L2. And just like our other regressions, you hit stat, then arrow to the right for calc, and then you're going to arrow down until you see sin reg. Okay, that is a sine regression that's going to do. And it will spit out the value in this format, a times the sine of bx plus c plus d. Okay, so that's what it's going to tell you as those parameters, a, b, c, and d. We can do the same exact thing with Desmos, so I'm going to go ahead and do that using Desmos here. So Desmos was going to look like this when I put the graph in. So you can kind of see how the curve is going. It's kind of seems to be going down, up, and then down. Think about what's going on here. If we continue this pattern on and on and on, this is not going to be like a quadratic. We'll go up and down forever in both directions. That's not realistic. Okay. It's not like it has a little bit extra curve to it. So maybe it's a cubic function that matches, but that's not realistic either. Okay. If I just model those real quick. So y1 is approximately equal to, we'll do a cubic just for the fun of it. Where am I at? ax1 raised to the third power plus bx1 raised to the second power plus c x1 and then plus d. So you can see it's not a bad curve, right? It's pretty close to that. And you look at some of the other values, like that r squared value tells us this, it's a really close fit. but it's not realistic for this because the temperatures in Chicago, though it may feel like it, are not going to dip all this way forever as time goes on, especially when we look at like the following June. It's not going to be in the negative values there. Okay. So instead, we're going to use this as the periodic function. So instead of using it as a cubic, we're going to just model it using our, just delete all this out here. Okay. We're going to model it using our sine function. So I'm going to do this pretty much the same thing that we have set up for our general format. So it's a times the sine. So I'm going to go to functions and click the sine button there. And that's going to be b, so bx1 plus c. And then now I'll do the end parentheses there, and then I'm going to add d at the end. And there it is. Really good fit and also realistic. Okay. The temperatures, the average monthly temperatures are going to be colder in the winter months, but then it's going to be higher in the summer months. Okay. So it's going to have that repeating cycle overall to help model that. So these are my values right here that we have. So we're going to go ahead and let's write that down now. Let's see here. Just want to make sure I have that set for myself. Okay. Give me 1 second here. Okay. So now I can write out my function. So y is equal to 26 point, let's just go with 49 times the sine of b is going to be a 0.49. And then x, we got minus 1.94 and then plus 58.25. Okay, so that is it for that one. And that's, again, that sine function that we get from that. Okay. So here's one more example. I'm just going to leave that for you to try that out. Okay. It's a bigger one, but we got up to 30 now in this case. So yeah, why don't we just pause it real quick? I'm going to go ahead and pause as well. Go ahead and do this real fast and then try out, see if you get the same thing that I get. Oh, 1 second here. Okay, so here's what it looks like when I have it all typed in. Okay, you can see it's not a perfect fit here, but I've got everything here for my regression that looks like this. Okay. Yeah, and so it's like you can see how the model doesn't quite fit, but it gets the idea across for what we're doing here. Okay. Again, this is the best fit because it has a periodic cycle to it. Okay. So, just make sure on some of these values here that I didn't mistype anything. No, it looks good. Okay, so that means I have my function now that represents the highs and lows of our the tides here. Okay, the high tide of each of these days over the course of, let's see here, in Canada for 1 lunar month. Okay, so that's that 30 days. Okay, so what I have for my equation was y equals, a was going to be 1.71 times the sine of 0.36 x, and then it's plus 1.67, and then plus 25.55. All right. And that's it. So again, today we're just focusing on modeling our sinusoidal functions using either transformation information, okay, or doing it with data and then doing a sine regression and function. Okay, so you can do either Desmos or graphing calculator, just whatever works best for you on that one. All right, and that's it for today. Take care, everybody.